Welcome, everyone. Today, we'll be presenting AuPPLE, Augmenting Physical Priors Through Language Enhancement using Self-Supervised Learning for Large Language Models. By now, we all know the extensive capabilities of large language models, such as GPT-3. They use vast amounts of data and powerful algorithms of weights and matrices to do complex natural language processing tasks, like understanding and generating human-like text. But how come when it comes to a basic question about the physical world, these so-called remarkable LLMs will fail? For instance, let me ask, how long will it take for a ball to reach the ground from a 5-meter tall window? From the top of our heads, we know it'll take 1 second, but for LLMs, it's not so easy. Large language models don't understand the physical world like us humans do. When presented with these problems, they simply regurgitate guesses rather than giving us an intuitive answer. This can become especially challenging for scenarios involving embodied agents or continuous control. So for our research, we have decided to dive deeper into this fundamental aspect that distinguishes us as humans, the intuitive grasp of the physical world that enables us to navigate through various situations like freefall and projectile motion. This way, we can try and replicate our inherent awarenesses of how the physical realm operates through fine-tuning techniques that can enhance latent physical priors for LLMs. However, beforehand, let's take a look at how other researchers have attempted to ground LLMs in the physical world. One intriguing avenue involves simulated representations of the physical world, demonstrated by frameworks like Pilot and MindSci. Pilot links language probabilistic programs to a physics engine, while MindSci similarly integrates simulations. Chain of Thought has also helped Math Prompter achieve this result. Although they have produced substantial performance improvements in the realm of physical phenomena, their main goals were to utilize external resources as a tool for physical reasoning. These simulators and chain of thought reasoning methods do not prove whether there's a way that we can set up a self-supervised pipeline to model the real world without physical reasoning. And so we propose our research question. Can large language models acquire an innate understanding of the physical world through meticulously curated fine-tuning?
We aim to significantly improve large language models' understanding of physical concepts and reasoning through a focused fine-tuning approach. By creating targeted datasets of physics questions and training the models to answer them, we sought out to enhance their intuition of the physical world. Thus, our methodology involved 3 key phases. First, we created a vast database of 10,000 short physics questions. Second, we trained large language models on these questions, utilizing a 90-to-10 train test split, with 9,000 questions for training data and 1,000 questions for testing data. Third, we evaluated the LLM's responses to the training set with the new and undiscovered testing set to see how well it could intuitively understand the physical world. This approach allows us to build and test the model's physical reasoning abilities effectively. The database we created had 3 different types of questions. First, we had continuous questions. These are your standard free response questions, where we only gave the LLM the question prompt and nothing further. When we were evaluating the responses for these, we ensured we were checking whether the LLM was getting within a specific range of the correct answers, because without computation, it was unreasonable to assume it would be exact every time. The next type of question we created were binary questions. These are your typical true or false questions, where when put in a 50-50 situation, will the LLM pick the correct answer? Lastly, we created multi-QA questions, which are multiple choice questions. We limited it to 4 choices for each question, and we used an algorithm on the back end to ensure that the answer choices were not too close to one another to accurately see if the LLM was truly getting an intuitive understanding of the physical world rather than just computing the answer. Now, how did we create so many questions? First, we created a set of template questions for both freefall and projectile motion. Then we wrote scripts that were able to batch produce these questions using deterministic equations so we wouldn't have to solve all 10,000 questions manually. These methods allowed us to create a robust data set to train the LLMs and further test them.
Our research incorporated the usage of various models. There's many LLMs that we fine-tuned and trained on our database. Slanty5, GPT 3.5, and 4, DBERTA and Roberta are the main ones. Slanty5 is a 248 million parameter LLM that we use in both training and fine-tuning. GPT 3.4, 3.5, and 4 are decoder-only ones with 175 billion parameters and over 1 trillion parameters for GPT-4, and we use them for testing our databases. Berta and Roberta are both encoder-only models, and we used both of them for fine-tuning.
As for the training process, we commence with a benchmark dataset containing 10,000 distinct physics prompts, each meticulously aligned with their corresponding answers, all centered around a specific physics topic, such as free fall and projectile motion. After that, we process our data using features such as sentence, answer, input IDs, attention mask, and labels. We take the initial dataset and perform data pre-processing to ensure its quality and suitability for analysis. Then we split up the data into the training dataset, which includes 90% of the benchmark, and the test dataset, which includes the remaining 10%. As for the training dataset, this larger subset is exposed to the model during the training process, where we take the selected language models, GPT-4, GPT 3.5, 25, Roberta, and Berta, and fine-tune them using the training dataset. After that, we take the selected language models and fine-tune them. And now for the model, once the language models are fine-tuned, they are primed for application. At this point, they should be adept at delivering contextually relevant responses that specifically tailored to the nuances of the provided physics prompts and the targeted physics topic. Finally, we evaluate. We employ the test dataset to evaluate the model's performance.
Our results show that it is indeed possible to ground LLMs in the physical world using only 10,000 examples in hyperparameter tuning. Displayed in this bar graph, our findings show that certain language models can have a sense of how physics works in the real world. For example, FLAN T5 consistently achieved over 3 times the accuracy on freefall and 2 times on projectile motion. Therefore, the notion that LLMs cannot have a physical understanding of the world with extensive training and fine-tuning is false. Our model also showed that this self-supervised learning is able to respond to prompts extending beyond its own question domain. This was proven through changing the form of questions from simple physics ones to embodied agent questions by switching the suffix and prefix. For example, the type of questions in this data set was changed from "a plate falls from," "how long will it take to hit the ground," to a physical world question like "you're the robot in a physical world and you see a plate fall. How long will it take you to hit you?" After evaluating our fine-tuned model through only generic questions on a 1,000 physical world and multiple choice data set, we were still able to achieve 87.7% accuracy, similar to the original test data set. Therefore, we know that a high accuracy was not just a result of overfitting through training. Testing on completely different data sets demonstrates that our model performs well in out-of-distribution data, meaning that results are transferable. For embodied agents, this can be especially useful in grounding to the physical world. A few patterns that we did pick up on with these models were, for example, we have 2 example questions where we can observe the different intuitive responses of different LLMs. GPT 3.5 seemed to randomly guess any of the 4 choices. Base T5 will always guess C when it doesn't know which is the correct answer. And our fine-tuned model will correctly respond to the question with intuitive understanding.
In conclusion, the fine-tuning pipeline we built on the principle of self-supervised learning has allowed an intuitive sense of physical reasoning. This shows that it's possible to ground an LLM on physics problems, which could possibly enable opportunities across different fields. The accuracy score we reached, which is close to an impressive 90% for both autoregressive and encoder-only models, strongly reinforces this observation. What's more captivating is that the model was still successful at answering questions even when it's phrased differently or presented in an unfamiliar setting. After fine-tuning on hypothetical freefall questions, the predictions we got on real-life freefall problems were still accurate. And this leads us to possibilities of future endeavors. We can ground similar LLMs on more advanced physical concepts. By incorporating more advanced physics topics and increasing the diversity and realism of simulations in the training data, models can develop more comprehensive and nuanced physical intuitions. Complementing the data-driven training approach with structured knowledge representations will allow encoding physics principles directly to enable more systematic reasoning. And applying intuitive physics models to interactive simulated and real-world robotic control challenges will demonstrate practical value and provide feedback for refinement. I believe this has the potential to be a very interesting application. Before we come to an end, we would like to express our heartfelt gratitude to all those who contributed to the success of this research endeavor. We're grateful to Blast AI for the exceptional AI bootcamp, making all of this possible. We also want to extend our thanks to our parents for their invaluable support all through this research project. Thank you all for being an integral part of this achievement. These are our references, and thank you so much for listening, and we're ready for questions.